And at this point, we just wait out the minute. So if you came into class, logged into Zoom right at 6 o'clock, my idea is you haven't missed anything. You'll be right on track. Unless someone asked a question and I'm still answering it, then that might be the only thing you might miss. Well, it's time. Welcome back, folks. Welcome to the fall 2026 semester. Welcome to ISU if this is your first semester. So it's been a long first day for me. This is my third class. Probably you're all in similar situation, but we'll get through it. 6 o'clock isn't too late, so usually it won't be too bad. We'll get more used to this as we go as well. So we have a lot to talk about to get us started, but I'm not going to try to spend the entire 70 minutes going through the syllabus. We'll try to make that short and sweet. I'm probably assuming that several of you have already peeked at it as well. One thing I want to mention right away is this is one of the so-called hybrid classes at ISU. It's two sections rolled into one. Section 20, I believe there's about 6 of us all together, is the in-person section. Section 30 is the online section, so that's why there's a Zoom session opened up and the Alcam are running. And for everyone that's here in person, you can see pretty much how everything works just from the projector. If you're coming in on the Zoom side, it's kind of mysterious what the setup really looks like. So I want to take a moment just to show for those in Zoom how it looks like from this side for you coming in as a student in Zoom. So here's what my view looks like in the classroom. It's kind of a limited real estate. There is only one monitor in this particular class. And so I'm going to be paying a lot of attention to a couple fields. I'll pay a lot of attention to, that's a little bit too big. Let me fix that. I'll pay a lot of attention to this section right here to let me know who's hanging around in Zoom. This will tell me who's currently talking. You can use reactions, those kinds of things. But I don't actually have a lot of space. This is where all the math is going to happen in the middle right here. There's not a lot of space to actually show individual people who are on camera. So you absolutely don't have to be on camera. It's going to be completely up to you. I don't think anyone is right now, so you probably already kind of understood that. You can participate in class if you're in person in the normal way, but because it's a Zoom class as well, and these Al cameras are starting to show their age, if you ask a question in class, I might have to sometimes say it back just so that it can make it into the recording. I've noticed that sometimes it's easy to have a question asked in class, but then when I listen to the recording, I could never hear the question. Or sometimes people in Zoom might say, what was the question? That kind of stuff. So it might be kind of annoying the first time. You might ask a question. I'll say it again just for the sake of people on Zoom or the recording as well. But if you have a loud, booming, projecting voice, then that's probably going to be just fine. But I think most people don't necessarily talk super loud when they're asking a question in class. So if you're participating, say, over Zoom on the online section rather than in class, you can use your microphone. If you're in a busy place or you just rather not, you can also participate using chat. If you use the chat feature, I'll read back your questions so it makes it into the recording like we said before. And this is actually a big challenge for me. There's lots going on in this screen, even though it's one screen. It's easy for me to miss when this becomes a chat notification. So if you send a chat and it seems like I'm just ignoring you or I missed it, you could just send it again. And anyone, whether you're online or in class, you could just say, hey, Mike, you missed a chat, and that'd be really helpful for everyone. So never hesitate to interject, especially if you believe you're probably right that I'm missing something. So that gives everyone kind of a feel how a class runs. It's kind of strange it being a hybrid class. Sometimes when I'll ask a question, I'm giving people a little bit extra time to respond, whether they're typing it out or formulating a response. So there might be 5 to 10 seconds of me just staring at you after I ask if there's any questions. But again, we get used to it. Well, I think that's my main thing I want to talk about right away, just getting used to the hybrid class. But I should turn it over to you for the moment. Any questions or comments at the moment from folks in class, in person or over Zoom? Okay, well, aside from the weird aspect that some people are online, it's a hybrid class, there's an in-person section as well. This is meant to be a fairly traditional class. There is no online homework system. There's a traditional textbook. You can get a web version if you want, or a hard copy, a loose leaf copy. And the way homework is going to run is in a highly traditional way. We'll talk quite a bit about the homework as we go through the syllabus briefly. You know what? We could talk about the homework right now. It's okay to do things out of order. Let's keep that thought going. The class is highly traditional, so it's meant to be kind of a pen and pencil type of classroom. For the textbook, you can see the syllabus. I guess we are opening it up. The edition we're using of the syllabus is through this particular ISBN. You want to be really careful with checking out the right edition because you can go onto Amazon for this particular class, put in all this information. There is more than one type of the 9th edition. Some of them have the sections completely scrambled, and it's really kind of annoying. So pay attention to the ISBN if you're buying this, say, a used edition over somewhere on the internet, because it's easy to get the wrong edition. It's not like information's missing, but your section numbers are scrambled, which can be kind of annoying. If you have the 9th edition, that's going to work excellent for this class. If you want to save some money and get the 8th edition, that will work too. You could potentially save hundreds of dollars. These are not cheap textbooks. So if you have an older edition, here's what you would do. You still have to do the same homework assignment problems, but when you click on assignment 7.1, I always will be attaching a PDF to tell you which exact problems that you're really doing. So if it's an older edition or maybe a different 9th edition, that's kind of annoying. These are the specific problems that are going to be assigned and graded for the class. So you could download this, you could print it out, you could work on this digitally, take ordinary scratch paper and work on it. It takes a while for that to load. Usually you want to click on that. Sometimes that's faster. So these are the problems directly out of the 9th edition of the textbook. So these are the ones that are assigned. And I give the page number for the 9th edition, the list of problems. Sometimes I have bullet points that could be hints or just expectations for full credit on each assignment. We'll be solving these problems as well in class starting out today, so you'll have a good idea of what the step-by-step solutions really look like. And there's a long spiel down below here. I'm not posting this on every assignment, but because it's a hybrid class, I just want to give everyone an set of options for how you would do the homework. You can do your homework in these 3 different ways, or you could get more creative. Maybe you could write out 4th options. One is, if you want to go really traditional, just take ordinary lined notebook paper, put down the section, go problem number 3, solve it, problem number 5, solve it, show the step-by-step solutions, and so on. If you like, if that's convenient to you, you could just print out these files and then just solve it on paper with a pen or pencil. Pen for the brave. Usually I'm using pencil when I'm learning something new. If you're working digitally, even in the classroom, several people have laptops, access to technology, and you like digital tools like a digital pen, then you're welcome to just download the file, mark it up. That sometimes is a convenient way to go, save it, and then you're all set. So whichever way just makes sense to you, it's going to work just fine. Either on paper or digitally is always going to work. For turning in your homework, you can just drop it into Canvas. You can either say, if you did option 1, take a scan of your work. Cell phone pictures are just fine as well. If I can read your handwriting, if I can read the image, then I'm not too picky about that. So if you worked it on paper, then just scan it, take some pictures of it, and then upload the assignment into Canvas. And that would always work just fine. There's an upload field for every assignment that you can use for Canvas. And if everything goes wrong with Canvas, for example, it was hacked during finals week of spring semester, if anything at all goes wrong with Canvas, I can just accept your homework by email. If that's your preferred way to send in homework as well, that always will do just fine. So if you like just emailing it, that'll work. Option 3, This is more if you're in the in-person section. If you're writing it out on paper and you don't want to scan it and send it to Canvas, you can just drop it over here on the table at the start of class, after class. And that's a completely acceptable way to submit your homework as well. You don't have to upload anything to Canvas if you don't want to, mainly for the in-person section. The online section probably doesn't want to drive down to drop down homework. So those are 3 ways you can do the homework, 3 ways you can hand it in. Any questions or comments whatsoever about homework so far? Okay, again, it'll be a pretty traditional class in that sense. Instead of worrying about other systems like, say, what are they called? WebAssign, MyLab, there's a bunch of other ones. This one, I think, will be a little bit easier experience. I think it's worth me taking the extra time grading so that we don't have any of the hurdles with technology. I think it's a better experience for learning calculus, particularly at the Calculus 2 and higher level. So that's already a pretty decent chunk of the syllabus talking about the homework as well. Other things I want to mention, again, we're not going to read it line by line, but let's just carefully highlight some spots. Interject at any point in class or on Zoom or with chat if you have any questions. One thing I should mention right away is just ways of getting a hold of me. You can text me, leave a voicemail message, possibly call me, although my phone is usually silenced. Teaching classes, I forget to unsilence it often. Best way to contact me would be just by email. You can email me at any time. It's never going to annoy me if you're just up late working on homework. If a question comes up and you want to send it out, just send it out. That's the best time to write it. So I accept email at any point. I'm usually replying to email starting my day around 8:30 a.m. and between classes. I usually don't reply to email after this class because I want to make sure I have a fresh mind when I'm answering your questions. But if you send me an email again, 9 p.m., 10 p.m., 3 a.m., that's always going to be totally fine. I'll just get to them as soon as possible. And I want to emphasize as far as email goes, because my office hours don't always work for everybody, you can send me anything in the email. You could ask for a hint on a problem. It could be something about the textbook, something about the class, upcoming exam. If you imagine you're working on a homework problem and this is your homework problem, but you're stuck, you're not sure how to get to the answer, you could just take a picture of it, send it to my email. I'll use the digital 10 to mark it up potentially, and I can work with you in that way as well. So you can use this as a kind of impromptu office hours. It's a slower turnaround than showing up in person, but it works. And if you're starting your assignments a little bit early, it gives you plenty of time to send me a question, get some feedback before a due date comes up. Other ways to get a hold of me are just through Zoom. For those who showed up online through Zoom, it's going to be the same exact Zoom link and Zoom password that you used to join class. For the in-person section, that's the link to join Zoom. So you can join office hours through Zoom in this way at any point. I have office hours on, oh, that's class meetings. I'm not sure where I was trying to highlight. I have office hours. That's the right thing right here. Monday, Tuesday, Thursday on Zoom from 2:45 to 3:45. Wednesday, I have office hours from 1 to 2:15. And if none of these times work for you, if you want to meet in person, just send me an email. We can make that happen. Usually I'm doing office hours in my office, tab 268. So if you'd rather meet in person rather than over Zoom, that will work out just fine as well. So those are ways, highlighting the right things this time, to get in contact with me. Any questions whatsoever about extra help outside class? Okay, well, Calculus 2 is a pretty fast class. It's 4 credits. We'll be meeting 3 times a week. I'd say the best way to really get through these sections, these class weeks, is start early at looking into the section that we're about to work through. You'll notice on every assignment, I put down a statement that goes, let me open it, read a particular section. There's a big part of this section that we're not covering. I'll say that there as well. And this is giving you a good idea of what the workflow would look like to be highly successful and as efficient as possible in this class. Before coming to a class where you know we're covering, say, section 7.1, which would be Tuesday and a little bit on Thursday, try to read as much of that section as you can, even if it's light skimming. Anything that you look at is going to prime your mind for knowing what's going on when we jump into that section in class. If you're seeing that information for the very first time as we're going through the lecture notes, it's a lot harder to really follow along and retain that kind of information. So any kind of pre-reading you do, even if it's, say, at a very low skin level, is very, very helpful. Then we'll go through those same exact problems directly in class. The solutions will be posted right here. They'll be available as a recording if that's a helpful resource as well. You can now use these as kind of a guide so that when you go back to the homework assignment, you can see how we solve some problems. In the reading, you'll see other examples and solutions as well. So pre-reading, coming to class lecture, doing the lecture actively, asking questions, writing things down. You're already learning quite a lot of stuff. And then when you jump into the assignment 7.1, it's going to be a lot more efficient. These problems aren't going to look like just brand new cold questions you've never seen before. And now you have to take a lot of time to say what's going on, reverse engineer everything. You'll already see related problems that we've solved, and homework is going to go a lot smoother. If you get caught up on any problem, if something just looks weird, not sure how to approach it, that's when you can come see me for extra help. I'm very happy to give hints by email, by office hours, over Zoom or in person. So that's the basic way the course is going to operate. I have other things to talk about in here. We kind of got through the homework as well. We should spend some time talking about exams. But any thoughts or questions so far? Okay. Other thing to mention is online sections at ISU's math department are kind of weird. They advertise this as being an online section if you're in the online section, but then the math department immediately comes around and says all exams must be done in person. So even if you're in the online section, the idea is you'll be doing your exam either in the Pocatello Testing Center, Idaho Falls Testing Center, or maybe for the remote Twin Falls, Meridian, North Idaho College areas, those kinds of things. I'll be working with everyone starting on Monday of next week when the registration for the class kind of solidifies. I'll directly contact you to determine where your preferred testing center will be. If you're in the in-person section, the assumption is you're probably going to test here in the classroom. If you're on the online section, we'll get it worked out. So we'll all have 3 in-person 75-minute exams and 1 comprehensive 2-hour final exam. On the syllabus, there's a schedule down below for the exams. These are the firm dates. The sections, if we take a little bit of time on one section or the other, the section dates on this day-by-day schedule are tentative so that we can have some flexibility. But the only things that are firm are the 3 exam dates and then the final exam. For the in-person section, the final exam is going to be on really awful time. This is the registrar's fault. It falls under Monday, December 14th at 8 p.m. going to 10 p.m. Really kind of awful, but I always work out a deal with everyone. If that's a bad time for people to test, I can offer other alternatives so that you're not going to be too worried about being forced to test when you're possibly not at your most mentally alert. We can work little things out to make that better. But that's the official time from the registrar's office. Well, that's how exams are going to work in class. All exams will be closed book. We'll be allowed a page of notes of that size, both sides, either handwritten or machine typed. A calculator is allowed on exams. It can't be a graphing calculator. That's the only type that's forbidden. But any basic scientific calculator will do just fine. These are just the 2 more often cited ones. This is the one that you'd have to use in, say, a lab setting. This one's a little bit more convenient. I'd select a scientific calculator. You can put in a long line of stuff just for the sake of efficiency. But if you're really good at that calculator, it'll do the job. Oh, looks like I missed a chat. Miranda says, is 1 8.5 by 11 page of notes for the test, including both front and back, or just the front. It'll include both the front and the back. And just to add a little bit further, that's going to be your standard letter size. So if you have, say, notebook paper, just know your paper might be a little bit smaller. So yeah, it's going to be both front and back. You can print out your notes. You can handwrite your notes. It's going to be how you like them. It'll be completely up to you. I'm not going to be collecting these notes at the end of any one of these exams. So even after you're done with exam one, I would encourage you save those notes. Save your exam one notes, your exam two notes, your third exam notes. The final exam is going to be one page as well, so we'll have to do some condensing to put it down. And if you notice what notes you really used on exams one, two, and three, you'll find that that's actually plenty of real estate on the final exam as well. It'll inform you on what to include. Well, any other questions or comments about examinations or otherwise? Okay. Well, another thing to talk about is kind of the breakdown of the grading system here, which goes a little bit into how the philosophy of the class was designed in the first place. The way I've designed this course, I've taught it quite a few times, but I always kind of work in sort of a bottom-up sort of fashion. What I know is what has to be on the final exam, what the course objectives are. And so I think about what must go on the exam, and I try to write my exams one through three that's going to support the final exam. So as you get through exam one, exam two, exam three, you'll have a very good idea of what final exam questions are going to look like. Those all together are considered a pretty good review of the final exam themselves. But then when I go to write my exams one, two, and three, I base it off what you really did in the homework. And I'm basing what I write down for our actual lecture problems right here on what I had signed in the homework in the first place. When I signed the homework problems, I wrote my lecture notes around them so that I made sure I was supporting the homework in the very first place. So all that all says is, if you're showing up to class, doing the pre-reading, getting through the homework assignments, if you fall behind, that's okay. You can still get caught up. I'm not going to penalize on late assignments. I will still accept them at full credit. But if you're working at a great pace, keeping caught up with the homework, working on them at a high level, you're already going to know what's on exam one, two, three, because it's going to be the similar type of problems. It's not going to be the exact problems. I'll change the numbers around. The functions aren't going to be the exact same, but it's going to be very, very similar in spirit. That will get you well supported on getting through exams one through three. But then final exam, it's not worth a lot, 25% compared to what it could be. We're allowed to drop those a little bit lower these days with the math department. It used to be like 35%, which felt like a gut punch. But if you're getting through exams one through three in a reasonable way, the final exam is going to feel more like a formality. It's something the math department just makes us do. It'll just be a way to solidify knowledge, review the whole course at once. So that's the idea with the grading. The breakdown heavily emphasize homework. That's worth two exams altogether, but that's because that's what's going to really get you to internalize this kind of knowledge. It's all about the work that you do out of class that matters really the most. So when you're solving these homework assignments, kind of imagine this is a real exam question. Try your best to solve it without any support. Then, if you feel like you need to look into extra formulas, extra advice, extra guidance officers, and so on to make that solution perfect, you're essentially just studying for your exams one through three. So working on the homework on a high level is really going to help you a lot on the way through getting through the exams. And that's pretty much my whole spiel about the syllabus. There's a lot more to read here, so I'm going to leave that up to you for further reading. There's pages of statements written by the math department. You've probably seen these similar kind of statements from other departments as well and your other syllabuses. I would definitely scan through here. If anything just seems a little bit off, say academic integrity students conduct statement, or this is something that you should read in just about every one of your classes. There's always an avenue for grievances. If something is just not going on right in one of your classes, you'll know what that something is when it happens. There are avenues to get that taken care of some way, somehow. You should be very familiar with the Title IX federal law, for example, and there's just pages of stuff here. So if you've seen these statements before, Title IX law hasn't changed, but if something seems completely new, I encourage you to definitely read that carefully. So I'll leave the rest of this beyond here up to your reading. And that will be our full run through on the entire syllabus. Which means at this point, we're ready to begin the course. Any last questions, thoughts, or comments or concerns before we get started? Okay, well, the experience of doing this class, whether you're in the in-person section or the online section, is I try to get to class, get everything set up about 20 minutes. Oh, hang on, I'm saying that wrong. I forgot. This semester, I have a class that goes from 4:30 to 5:40. So I'll just be in this room after my prior class ends and I transition into the new class. If you join Zoom a little bit early, you might see the last end of my prior class, or if you walk into class a little bit early as well. But that's okay. We're just transitioning over to the calculus class. As soon as I get everything set up, I'm happy to take questions. And I'll get us scrolled down to whichever section that we're currently in. So today we're in section 7.1, integration by parts. Before we just delve into those new concepts, I have a couple examples where we're just kind of doing a soft review of some important concepts that connects over from Calculus 1. So let's take a look into those. Here is the 7.1 notes. And maybe just another piece of advice for participating in the lecture, taking notes and those kinds of things. There's also a lot of ways that people feel comfortable doing this as well. Some people might want to download these notes. There is both the Word file and a PDF version in blank lecture notes. This folder is important because we're going to override this with our solutions. So if you need a blank copy and that one is filled out, just go to the very top of the Canvas page. So some people would like to print them out, fill them in, or maybe download them to your machine and digitally fill them in. Some people are comfortable just having a ordinary tablet out in a more traditional way and just labeling things example 1 or example 2 part A and solving them along the class. And week 1 is a good point to kind of just feel comfortable about how you would like to work in class. But the more you can do, the more you can involve more of your senses, not just seeing, but seeing, writing. The more involved you are with this kind of material, the easier it is for this to just snake its way into your mind. You might start dreaming about this kind of stuff if you're reading it, solving it after class, working hard on it during class. It just becomes something you can't help but learning when you are that active. So here's where our entire course is going to start. We're not at integration by parts yet. This is some connective material here. One of the sometimes foggier ideas in Calculus 1 and Calculus 2 and Calculus 3 and vector calculus is sometimes the idea of the differential. It's an algebraic structure where you take a function, y equals f of x, and you write down an equation that has really 3 different kinds of variables. X is an independent variable, dx is an independent variable, dy is the dependent variable. So we start with a differentiable function. We can indicate it to y equals f of x. And when we say specifically the differential of y, we don't mean the derivative, although it's part of that entire structure. The differential is an equation now. It starts off by matching dy with the variable y that we had. It puts in dx on the end, and the derivative goes here. So the differential is not the derivative. But you throw in the derivative as part of it. Let's just say derivative is a component to the differential, which is nothing but a particular kind of equation. It's a useful formal structure. It's useful for integration. And that's where Calculus 2 spends a lot of time. Calculus 1, we spend a lot of time about differentiation, applications to differentiation, and not so much on integration. So this is where we're picking up on the integration side in Calculus 2. So for the sake of a review, let's do a differential right away. The variables matter. So we have v equals u times tangent u. So here's the part in blue. The variable is u. I'll just highlight that whole thing in green. We need correct mathematical notation. So whenever you're asked to compute a differential, what we mean by that very specifically is there has to be a dy, there has to be a dx, and we consider that dx an ordinary variable, so it interacts as an algebraic structure in the normal way. For example, if our derivative is multiple terms, you do need parentheses now to write down that equation. You could distribute dx through it, or just leave it factored out. So here's how we would start here. If we have v, we're writing down the differential, we must have dv. So that's a good start. Next, we have to throw on the derivative. This will be the derivative with respect to u. And we need to be careful with this. Here is the product rule that we must use to differentiate that thing. Let me start with the parenthesis. And the product rule, the way I typically go is, and you can change your strategy to whichever you're most comfortable, I typically just differentiate the first factor. Take the derivative of u, which comes out as a 1. I'll throw it down here in the notes just as a paper trail, but that's going to simplify pretty fast. Copy down the other factor, tangent u. Go plus for the product rule. I'm going to copy down the first factor, u, and then differentiate the second factor, tangent. Derivative of tangent becomes secant squared u. Then we multiply the whole thing by du. Let me fix that pen. And just to simplify it, because it looks strange with writing a 1 times, that definitely simplifies to dv equals tangent u plus u secant squared u du. So that would be the differential. Notice, like we mentioned before, brackets is necessary for this one, because if we drop brackets, it doesn't have the right meaning. du is allowed to multiply everything inside of here, in other words. So that's kind of a throwback from maybe when you're doing u substitution in a Calculus 1 situation. Any questions at all, folks, about the differential? Okay, some elements of this are more trickier than the others. Sure, the differential is kind of a strange looking equation when you go to write it out, as lots of moving parts, more than you expect. But notice the product rule is involved, and maybe even more concerning, we just have to know that if you take the derivative of tangent, you get a secant squared. So that's review material from the Calculus 1 days. And if that just seems kind of foggy, that's what the purpose of this file is. This is a file of information that we have to be ready to go with in a Calculus 2 class or a Calculus 3 class, differential equations, and so on. Let's open this one up just for the sake of review, which is kind of the theme starting us out today. As far as the differentiation rules go, it's also formulas. Here are some of the standard differentiation rules that we all know and love. Derivative of a constant is 0, for example, or we just use the product rule here. Again, I have it in a slightly different format. I like to take the derivative of the first term first, because it reminds me how to do this one correctly. And if you look at that really carefully, that looks like a typo, doesn't it? That should be, I don't know how I missed that. Right there, that should have a negative sign. So I'll make a correction to my notes right here. I don't think I have the file available with me, or I'd correct it right now, but I'm going to re-upload that. It's going to say revised, and we'll make sure we get the quotient down, rule down correctly. Sorry for the distraction on the very first day of the notes. But hey, if you spotted that, good on you. I would consider that some pretty decent review on its own. Then scrolling down beyond that pretty critical typo right there, we have the good old chain rule. And These are easy to get kind of slippery, especially if you took, say, Calculus 1 in the spring semester. It's been a long summer. Keep in mind, these derivatives we have to just be at the ready with. We took the derivative of tangent and got secant squared, but we know from integration, that's a double purpose formula. The antiderivative of secant squared is tangent x. So in other words, we can think of that row right here as also saying integral secant squared x dx is tangent x plus a constant. So these are very, very critical formulas. In a Calculus 1 class, I always encourage people to get these memorized down pat. If you do have them completely memorized, good on you. This makes everything much more fluid, easy to get through in both Calculus 2, Calculus 3, and beyond. The last thing you want to do is every time you differentiate any one of these functions, have to always go back and look it up. After some point, you are going to memorize it after looking them up over and over again. But the sooner you get these in your mind, the better. Hyperbolics can also come up. This is nice because the only difference between the table is where the negative sign went. On this table, whenever we took the derivative of a cofunction, we outputted a negative sign, but that's the odd one out. The derivative of hyperbolic cosine is hyperbolic sine. Inverse trigonometric functions also come up. This is a harder table to memorize. So this one, I mean, no card is a pretty good strategy for this, but they do come up. They come up quite a lot in Calculus 2. We might have to sometimes integrate 1 over 1 plus x squared, or some kind of variant of that. These come up quite a lot as well. And so trying to solve this from scratch, some crazy u substitution, some weird trigonometric substitution, it's just going to be a nightmare. That if you know that this is a formula that's just ready to go, that's the purpose of these notes, to collect in one spot all of the really, really important carryover formulas that you need for Calculus 2. If you're going into exam 1 and you just want extra insurance, maybe this table feels kind of foggy. I'm not policing what you put on your one page of notes on the exams. This is decent stuff as well. Keep on scrolling. The logarithmic function derivatives are here, exponential functions, generic exponential functions, and that's the end of these notes. But it's really these tables right here where I really would emphasize you really want to have these just ready to go with in the back of your mind. And that's where we used it. We just have to know derivative of tangent comes out as a secant squared. Okay, that's a long spiel. For our example 2, we're going to review a little bit of integration, and then we'll start looking into integration by parts. But any questions or comments at the moment with anything we've done so far? Okay, well, this next problem is really section 5.4. That was the u substitution concept in Calculus 1. And by the time you're finishing off Calculus 1, I feel like it goes somewhat fast in chapter 5. So this is one of those topics which is massively useful, worthy to review. I mean, section 7.2 in our class is going to be u substitution after u substitution. So this is a good opportunity for us on day 1 to just review that technique. Here, this is an indefinite integral. It doesn't say from 0 to pi, for example. So the answer is not the area under the curve. The answer is the most generic antiderivative. We'll use a constant c for integration. So to solve this, because it's a function times a function, we cannot formulate the answer by just taking the antiderivative of x times the antiderivative of sine x squared. You could check your work. It's not going to work out if you attempted that. There's even more going on. If you differentiate sine x squared, that's the chain rule. If you notice the chain rules are part of your problem, then that's one giveaway. It's probably a u substitution scenario. So here's how we would set up this. In u substitution, sometimes we try to look for what is an inner function. What's a function going inside another one? That's not the only way it could be used, but sometimes that's a pretty good big giveaway. We have x squared going inside the sine function, sine composed with x squared. So that's a good suggestion to just let u be x squared. So after we've decided all on what our u should be in u substitution, the next step we always must take now is take the differential. That's where example 1 clicks in, our review of differentials. So when we take the differential of this u, we would get, just deciding on how I want to color code that. I'll write it as du equals, take the derivative of x squared, nothing major, just a 2x. Remember, there's multiple moving parts on a differential. Our variable is x, so we'll put a dx on the far right. So now we analyze the integrand, x sine x squared. The 2 is the odd one out. It's not represented there. So one strategy that is often used by our own author in our reading is to just divide this bona fide equation by 2. You could rewrite this as 1/2 du equals x dx. So reason for doing that is, now x dx, it's part of our integral. X is part of the integrand. Dx is just indicating what variable to integrate with respect to. And although you don't have to take this step, sometimes it's not a bad idea, just for the sake of organization, to rewrite it as sine x squared times x dx. I mean, that's an extra step. But sometimes, in particular section 7.2, it's worth the effort when there's a lot going on with the u substitution. X dx, we're going to just rewrite as a half du. Sine x squared, we're just going to rewrite as u. So we reused our table on the right to make our substitutions happen. So on the next step, we're integrating. Now let's actually put in those substitutions. This becomes sine u. So one substitution already. X dx is a half du. We can work with that 1/2 right there. We can leave it inside as the integrand. But one property of integration says you can move constants off to the left. That's our nice constant multiple rule. So we can put that 1/2 here and then throw in du here. So following the color coding to the right column, where green turns into these components in blue, that's our new integral to work through. And this is essentially the major strategy for the first half of chapter 7. Well, maybe more than the first half. We took something that's a harder problem, section 5.4, and this is now reduced to a section 5.3 type of problem, where all we're doing is finding an antiderivative. So that's our next step, get the antiderivative of sine. And let's pause and think about this one. Any volunteers for what the antiderivative of sine should be? Yeah, absolutely. From class, it's negative cosine, and good call on that negative there. Since it's a negative cosine as the antiderivative of this, we need to put in negative 1/2 cosine u du. Let me see if I can collapse this a little bit better. So the derivative of cosine is negative sine, but we're trying to find the antiderivative of just sine itself. So imagine the negative has moved off to the left-hand side, and that's the way the integration goes. Or maybe even a better thought. All we're trying to do is come up with an antiderivative. So you can check your answer just immediately, right here as it stands. Take the derivative of negative 1/2 cosine u. Constant multiple rule says negative 1/2 stays where it is. Derivative of cosine, that's negative sine. So we have negative times negative, comes out positive as intended right here on the prior step. These are easy to get kind of mixed up. It's really easy for me to go from sine to cosine, forget the negative sign. So if you ever notice, I'm just kind of staring off into the right and upper. I'm just trying to recall, where does that negative go? Because I'm not going in the differentiation direction. Reverse the direction. You need to be really mindful about that negative sign as well. That's great progress. But as you know, u substitution is never over at this step. We have to undo our substitution. Let me make that u a little bit easier to read. So we rewrite this u we see here as x squared, and our job is done. So the answer is -1/2 cosine x squared. And that was a really weird thought right there. I'm not sure why I put down a du. Let me put down a red, a little bit of a correction. When we're finding an antiderivative, we're looking for a family of antiderivatives. Infinitely many different functions that differ by just a constant. I'm going to chalk this one up to being tired. And also for correct integral notation, once we find the antiderivative of something, du goes away. That's just telling us what we're finding the antiderivative with respect to variable u. So du vanishes at this step. So it should just be the constant of integration plus c, undo the substitution for x squared, and go plus our constant c. Then that's the full process. The differential up above was just a vehicle to help us unwind this result right here. Now, if you check the answer by differentiation, you're using the chain rule, you'll get back x sine x squared. Well, we did it, folks. That's our first antiderivative for the day. When you go to format your answers, say for homework, for exams, it's okay to leave it just like this. But sometimes if you feel like it doesn't flow from question down through equalities to answer, because maybe this side work got a little bit too close to your end answer, never harm to box out your answer. You don't have to box out every single answer, at least unless that's just something you do. That's completely fine then. I think we all get that kind of beaten into us from earlier education days. But box it out definitely if it feels like there's a lot of work just in a compressed spot. I'll try to always do the same. I'll try to format my answers better so that the side work and the end answer don't get too close to each other. I think I was just trying to get the differential revealed above as we finish this one of here. So there's part A. That one was the bigger problem for the notes. Next couple one that we're looking into are kind of trick questions here. A little bit of a thinking question in a certain sense. X sine x as an integral, you need integration by parts to solve that one. But that's not all that's really going on with this one. This is saying take the antiderivative of the derivative of x sine x. If you wrote that out in Leibniz notation, you'd be saying, what is the antiderivative of the derivative with respect to x, d dx, of x sine x? Antiderivative with respect to x means put in a dx here. So it's a kind of a weird amalgamation of symbols when you look at it. But the more you think about this one, the more it looks like there's really an answer that's just sort of staring at us. Could follow ordinary of operations and actually differentiate this thing. Product rule will come into play, and you'll get an answer, but it's still going to need integration by parts. It's still not easy. But reading this left to right, it's saying, find the antiderivative of the derivative of something. Well, if I already know what I'm differentiating, x sine x, and it's asking me to find the antiderivative of that, the answer is just x sine x. That's the particular antiderivative. We have to put on the integration constant plus c. Well, that's the whole answer to this one. It just feels like a weird trick question, but sometimes these sort of things, they do pop up in our work. This kind of thing actually comes up in our derivation for integration by parts. So it's a useful, weird little problem to take a look into. So the words, the antiderivative of the derivative is just the thing you were taking the derivative of in the first place. Or maybe a nice kind of visual way to think about this is the integral operator here is just antiderivative. That's the differential operator. It's not exactly a cancellation because we have infinitely many answers, the plus c, but visually that's kind of what's happening. It's a type of cancellation. One has undone the other, in other words. So that's all that's going on with part B as a trick question. Any questions or comments with getting through that one? Okay, again, a lot of these problems are just kind of connective material to help us transition into Calculus 2 from Calculus 1. And part C, this one is really, really important in a big way. If you were to solve part C, here's a couple schools of thought on this one. It is a U substitution type of problem. But the U substitution on this one is in a real way different than the U substitution that we did in part A. Sometimes U substitutions are kind of complicated. They're not always very easy to unwind. For me personally, it's not easy for me in my head to go x sine x squared down to negative 1/2 cosine x squared. That one I'd have to stare at for a while, and probably U substitution is just more efficient for me. But there is a whole class of problems that come up a lot in this class, so often that you wouldn't want to use U substitution every single time, and this is one of those. Our author in the reading is often going to say, take a mental U substitution. Let me be a little bit more descriptive by what he's trying to emphasize. If the input to sine, or e to the x, or the square root of something, if the input is a linear function, it sounds strange, but it really is highly encouraged to skip U substitution. It's a lot of steps on the side work. It's a lot of steps running through the process. But if it's linear, there is a very fast way to solve this in just one shot. So that's what we're going to do. Input is a linear function means, just as you'll see in the reading, we'll do so in class. That implies we will skip the U substitution process. I'll just abbreviate that to U sub. Now, let me show you the logic on how we'll do that skipping. That's about that constant multiplier 3 right there. We already know from part A what the antiderivative of sine is. It's a negative cosine. So we go from there. This is a sine with a little bit more inside, but still it'll be negative. Give it a little bit of space and write cosine. 3x will go inside there. We'll add our ordinary constant of integration. But then we pause right here. There's always a built-in check to this. If you differentiate cosine, it's a chain rule. You'll differentiate the outer function first, cosine. Its derivative is negative sine. That negative cancels. But then you multiply by the derivative of the inner function, 3x. The derivative of the inner function is 3. Because there is no 3 right there, we counteract it by dividing by 3. So we divide by 3 in that way, and our work is 100% complete at that step. This is why we would skip the U substitution at this stage, is because these come up so often that if you did a U sub every single time, your hand's going to get tired for one in certain problems, but you're kind of denying yourself a lot of time to move forward into the real topics of that particular section. But just to emphasize, let's differentiate our answer right here and now just to show the other side of this logic. If there's a constant multiplying, we divide by that constant, and we just treat that as if it was sine x. Just divide by that constant 3. And we can mentally check, or just write it in the margin, negative 1/3 cosine 3x prime. Constant multiple rules first says negative 1/3 multiplies the answer to the derivative of cosine 3x. We work outside in. 3x is the innermost function, so we differentiate the outer function cosine first, which will give us a negative sine. We throw in 3x as an input. The chain rule says you must now multiply by the derivative of that input. We're chaining on a derivative, so we multiply by 3. And that's where all the nice cancellations happen. That 3 and that 1/3, they cancel out. The negative signs, they cancel out like we expected from part A. And so it told us that we don't have to work hard every single time u substitution comes up. Sometimes it's all about dividing by a constant. Does not work on that one at all. If it's a different function, x squared is not linear at all, it's quadratic. Any other thing inside of sine other than linear, that whole method is off the table. And that's the case where we'll always show the direct steps top to bottom on u substitution. Well, part C, again, it comes up enough in this class that that's a good one to talk about. This is actually going to come up a lot in just these notes alone. Any questions about solving part C? Okay, we'll have one last one as a review problem, connective glue from Calculus 1 to Calculus 2. This one's a trick question, but it's a different trick question from part B. Let's make this one our last question for the day. Since day one, we've already done quite a lot. There's a lot to kind of internalize. I don't want to throw too much at you. We'll usually be ending class right around 7:10, trying to give you some extra time for answers as well at the very end. But for today, just so we're not overloaded, we'll consider this our last one for the day. It's a good thinking question, so let's give ourselves about 30 seconds, take a look at it, and if you spot the answer, don't hesitate to say it out at any point. Okay, that was about 30-ish seconds. Any volunteers for what the answer should be on this one? Yeah, absolutely. Good call. The answer to this one is absolutely nothing but zero. And again, it's one of those tricky thinking questions. I think it was a good one for part D, mainly because we've been looking at indefinite integrals, right? But this one's different. This one is a definite integral. What makes the difference? There's a lower limit of integration and an upper limit of integration. If you're looking at a definite integral, the value of that definite integral is the area under the curve from 0 to pi of the function x sine x. I thought I had Desmos pulled up, but it doesn't. But we could imagine we could plot that to get a good visual. Let me just add down here. The answer is an area. We mean a signed area. If the area or if the curve went down below the x-axis, we were accumulating negative area. Then we go to the differentiation rules, and you know what? This comes up. This is the very first differentiation rule. The derivative of a constant, no matter how abstractly you write that constant, it could be the natural log of the square root of sine of 2. But that's constant. That's just a number. There's no x there. Or if we do all of that, it's just a number. It's a signed area. The derivative of the constant is always 0. Even though this is one of the first differentiation rules, it's the trickiest one in a lot of ways. You can disguise a constant to make it look like it's a function that varies in a lot of different ways. So that was the idea with part D. I don't think that's a trick question I would throw on an exam, but just a good thinking question to spot the difference between indefinite and definite integrals. So that's our kind of a fast review, just some of the main topics before we get into section 7.1. In section 7.1, we're going to find out how would you find the antiderivative of x times sine x. No tricks like on part B. There's no derivative sign. We're going to ask and answer, what would you do if it looked like that, just x sine x? The strategy here is going to be work really cleverly with differentials, involve the product rule just right, And that's all integration by parts is, a rearrangement of the product rule along with differentials. So we'll go through that really carefully. Tuesday, next class meeting, will be more of a full class day, whereas today was kind of an introduction, not a full-on day. But before we call it a day officially, any last questions or thoughts? Okay, well, thanks for all your feedback and participation today, folks. I think Calculus 2 is infamous in a certain sense that some of the sections are a little bit harder than some of the others, but it's also kind of a rewarding class. And once you get through Calculus 2, you're kind of over the hump. If you know you're taking Calculus 3, this is a great class to get through. If you get a great result on this class, you're just going to kill it in Calculus 3. So we'll be working through this course really carefully, day by day. The more you participate, ask questions in class, through email, through office hours, the easier it'll be to get through. But have a great night, folks. We'll be back to it on Tuesday. Thanks. Have a good one.